Okay, I just wanted to make a few comments about the book and maybe some other computations here before we get going. And that is, in the book is going to go through the undamped free vibrations, and notice that there's no damping there. And so we get our solution like we did in class or in the video of last time. And so we get this solution here. Now, I just want to be real careful here because our book is going to call this delta. Let's turn the page. It's called the phase or phase angle, right? And this is where we get into trouble, right? It measures the displacement of the wave from normal position corresponding to delta equals 0. Well, is that true? Is that where the cosine is equal to 0 or the cosine is equal to 1? The cosine is equal to 1 where omega naught t minus delta equals 0. So I just wanted to mention, let's get a piece of paper here. Just wanted to say, right, that if you set omega naught t minus delta equal to 0, your t is going to be not equal to delta, but delta over omega naught, right? And so this graph, this position right here should be delta over omega naught, right? And so that's why I'm going to distinguish between delta being the phase angle versus whatever this is, and that's going to be the phase shift versus phase shift. Well, I shouldn't say whatever it is. Phase shift is delta over omega. Yeah. Okay, and so that's just a quick note. It's hard to believe that the book has gone through this many editions with that in it, but that's okay. We've got it fixed, and so now you might notice while we're here, right, and for this model we have periodic motion, pure periodic motion, and so you can go through and look for the period, right? And then once we add in the gamma, we get the full set of solutions, and of course we went through the 3 cases, but I just wanted to look at some graphs of those cases. This is the case where we had the damped, the underdamped situation. Okay, and so that means we still have oscillations, but they're dying off, right? And so our solution looks like RE to the minus gamma over 2mt, right? And then we have this cosine of mu t minus delta. And so the oscillations are coming from the cosine function, and the exponential function is dampening the solutions down. Okay, good. All right, and then the last case was the overdamped. This is the critically damped. It's very similar in style to the overdamped. And so you see here, right, that in this case the solutions don't cross the t-axis, but it is possible for them to cross once. Okay, but you'll see here the difference, right, between like the underdamped case and the critically damped case, or the overdamped case for that matter. Good. And so what do you see on this page? Hopefully at this point you'll see that both of those are going to be underdamped, right? Or yeah, underdamped, because the damping factor is going to 0. Good. All right, and then of course you can figure out you can go through, and I think they're trying to figure out some of the periods and things in here. Notice that this function in and of itself is not periodic, right? Right, the solutions are going to 0, so therefore it's not strictly periodic. However, because of that cosine part, we're going to be calling it quasi-periodic. And so from the cosine part, you can read off the what the period's going to be and the shift, or the phase angle. We're going to start getting those mixed up. Good. We're not going to do anything with electrical circuits, although they're kind of fun to look at. I think that those require a little bit more physics than some of you have had, and I didn't want to take that much of a tangent. Good. Okay. I'm going to pause here for a second and set up the next thing I just wanted to talk about briefly, and that was what happens with the model. Let me see where am I going to pause here? Okay, so I wanted to talk about the solution. So in the general model, we have our roots to the characteristic equation were minus gamma squared plus or minus the square root. Oops, that was minus gamma. Gamma squared minus 4mk divided by 2m, right? And so this is where we were saying, right, if you rewrite that, that's going to be minus gamma over 2m plus or minus the square root of gamma squared minus 4mk divided by 2m, right? And now we want to remember that m, gamma, and k are all greater than or equal to 0. Actually, let's make them just greater than 0 in this case. Good. And so now, the first case was when we have two real solutions, and that's where gamma squared minus 4mk is greater than 0. And so notice in that case, right, then what is bigger? Is gamma squared bigger or less than gamma squared minus 4mk? Well, because the constants are all positive, right, gamma squared is going to be bigger than that. And so when you take the square root, right, these are positive now, square root of gamma squared minus 4mk, right? And so in terms of sign, SIGN, of this expression, right, what happens if you take negative of that? Geez, my computer keeps dinging. Do you see here that because gamma is going to be bigger than this, right, what's going to happen then when I take minus gamma plus or minus this quantity? I'm going to get two negative real numbers, right, when I compute this quantity. Okay, how about the when we look at the complex roots? In that case, we'll have minus gamma over 2m plus or minus. Now this is where the discriminant is negative, so I'm going to reverse the signs here. Okay, and now this is the real part. This is the imaginary part, right? And so you're always going to have that e to the minus gamma over 2mt times your cosine plus I sine, right, as your, well, we'll just say C1 cosine and C2 sine. I don't care about what's inside these parentheses because I'm really just focusing on this exponential function. The idea being here that all of our solutions are going to 0, right? And what happened up here? Because these have two negative real numbers, all solutions went to 0. And finally, the last case, do we still go to 0 if gamma squared minus 4mk equals 0? Well, in that case, our roots are a double root, right? And so we have e to the minus gamma over 2mt times c1 plus c2t. And in this case, right, the exponential function is going to kill off the polynomial. And so this will also go to 0 as t goes to infinity. Good. So in all cases, in the spring mass model, or mass spring model, however you want to call it, all our solutions go to 0 because our constants are all greater than or equal to 0. Right? You can't have 0 mass, otherwise you wouldn't have a second order differential equation. Okay, but that's I'm starting to ramble. Good. Okay. So I wanted to mention all of our solutions are going to be going to 0. Okay, we'll see you in the next video.